Hey YouTube, in this video I'll be going over a quick proof for the golden ratio. You can see it here. It's usually denoted by the Greek letter phi, and here are some digits. It is irrational, so the digits go on forever, but it's not transcendental, and we'll get to what that means a little bit later on. The easiest way to understand why the golden ratio is so important is by the golden rectangle. The rectangle where the ratio of the longer side to the shorter side is exactly the golden ratio. And the reason why this rectangle is so perfect is if you were to square this, and by that I mean if you were to cut off a perfect square from one side of the rectangle, sort of like this, what you would be left with is a square and another golden rectangle. So this rectangle would have the exact same dimension, or the exact same ratio of sides as this large one. And the cool thing about this is you could actually continue this process forever. You could keep squaring the rectangle on and on. So as you can see here, I've done a couple more iterations of drawing in squares, and if this rectangle actually were perfectly golden, I'd be able to do this infinitely many number of times, and it would result in a golden spiral of perfect squares. But for this proof, I'm only going to need to square the rectangle once, so I'll just leave one square here. And to make it easier, we'll also redefine y as just 1. We can make this rectangle whatever size we want, and if we have one side that's equal to 1, we know that x is just equal to phi, so it makes it a little bit easier. Also, I've labeled this side, this shorter side here, equal to a, and we know that this side here, because it's across from this one, also has a length of 1. So using the definition of the golden rectangle, we know that the ratio of 1 to a must also be the golden ratio. So we can go ahead and write that here. And one other final thing we can write from this figure is that this length here is also 1, because we know this has to be a perfect square, so it's a 1 by 1 square, and this length is a. So we know that 1 plus a must be equal to x, the length of the whole side. So we'll write that here. So as you can see here, we have 3 equations and 3 variables, so it should be easy to solve for phi. And one equation is literally just a substitution. So right away, we can substitute x in here, so we're just left with a and phi. So here we can easily combine it to just 2 equations and 2 variables. Here I've simply taken 1 plus a equals x, and I plugged it in for x here, and that gives us 1 plus a equals phi. And here I've rewritten 1 over a equals phi as 1 over phi equals a. These can just be switched around. And now we easily have 2 equations, and a is solved for here. So we can plug that in here, and we'll have 1 equation and 1 variable. So now you can see here, we just have to solve for phi. It's 1 equation and 1 variable. And the easiest way to do this is to start out by multiplying both sides of the equation by phi. So we're just left in quadratic form. So now you can see we have it in this simpler form by just multiplying all 3 parts by phi. And now we can just move everything to the right-hand side of the equation, so it's solved for 0. So here I've taken phi in 1 and I've just moved it to the other side of the equation. And now you can just use either the quadratic formula or completing the square to find out what the value of phi is actually equal to. And when you solve that, you'll get that phi is equal to exactly the golden ratio. It's important to note that the value of phi is actually square root of 5 plus 1 entirely over 2. And because it can be written in that form, that means that it's not transcendental and it's just simply irrational. So these digits are random and they'll go on forever, but because you can write it in a compact mathematical form, the value of phi, unlike something like pi or e, is not transcendental. So yeah, that's pretty much it. This is the whole proof. If you have any questions or anything else you would like to comment, feel free to write something down below in the comment section. And yeah, hopefully you guys enjoyed. Thanks for watching.